In this video, we'll be discussing the semantics of the universal and existential quantifier in FOL. We'll also be talking about some of the aspects of quantified sentences in FOL that need to be discussed in order to talk about the semantics of these quantifiers. Let's turn and take a look at it. All right, we're going to have two quantifiers in FOL. We're going to have the universal quantifier, and the symbol for the universal quantifier is that upside down A that I just circled. And what it does is it lets us assert that all objects of a domain satisfy some condition. So for instance, looking down here, the condition would be x is a cube, and this is saying that every object in the domain of discourse that we're talking about is asserting that all of those things satisfy the condition of being a cube. So as a result, we read the universal quantifier as everything or all things, and it indeed corresponds to the ordinary English locutions: everything, all things, each thing, anything, so on and so forth. So when we come across the universal quantifier with the variable, and we'll talk about variables in a moment, with a variable next to it, the way that it reads is, in the jargony way of saying it, is for every object x, for all x. Those are the two main ones. So again, looking at this quantified sentence, it says a couple of ways of reading it in the jargony way is for every object x, x is a cube. For all x, x is a cube. Or and now we're moving to the ordinary English, everything is a cube, all things are cubes, so forth, so on and so forth. All right, let's turn now to the existential quantifier, which is the other quantifier in FOL. All right, the symbol for the existential quantifier is this backwards E. And what it allows us to do is assert that there's at least one object that satisfies some condition. So again, if our condition is x is a cube, then to have this existential quantifier with an associated variable, that's telling us that there's at least one object that is a cube. The way that we read the existential quantifier is something, and indeed it corresponds roughly to the ordinary English locutions: something, some, at least one thing, a, and so on and so forth. All right, so the existential quantifier associated with a variable reads as for some object x, for some x, or there exists an x. And I'm a fan of there exists an x because it makes overt that the existential quantifier commits us to the existence of some object having some property. All right, so our quantified sentence here, the way we would read that jargony, we have a few ways. For some object x, x is a cube. For some x, x is a cube. Or there exists an x such that x is a cube. In the ordinary English, we would read that as asserting something is a cube, there is a cube, so on and so forth. All right, so we've already seen that our quantifiers will be associated with variables. And not only that, but as logical operators, we've seen that they operate on things that look much like sentences, but are in fact just well-formed formulas. So we need to take a closer look at variables and well-formed formulas so we understand them better. All right, so for variables act very much like individual constants. So here we have an atomic sentence: A is a cube. A is an individual constant, And what it does is denote an object. So it picks a specific object out. Our variables will end up in the same placement as individual constants do, but they don't denote a particular object. Instead, what they do is they range over the objects that we're talking about. So suppose that's a cube, a tetrahedron, so on and so on. So X is ranging over all of the objects in the discourse that we're talking about. I'm sorry, in the domain that we're talking about. All right, so the other thing that it'll do for us is it'll serve as a placeholder that informs us about how a quantifier is operating on a well-formed formula. So in this case, that well-formed formula is within the scope of this quantifier. And it's telling us that it's operating on that quantifier, it's operating on that well-formed formula in a way such that it's saying that there exists at least an X that has this property, being a cube. So it says there exists an X such that X is a cube. And then what we do is we go to see the domain of discourse and look at all of the objects that X is ranging over and see if there are any that are in fact cubes. In this case, we have one that is a cube, so that means this sentence, what it is asserting, is true. If there wasn't any cubes, then it would be false. All right, so FOL, we have an infinite number of variables in them. We start with the letter T, although T is usually reserved for time, so time as a variable for time. But T is a variable, U, V, W, X, Y, and Z are variables, and then we get an infinite amount of them because we just go sub 1, T sub 1, U sub 1, V sub 1, W sub 1, X sub 1, Y sub 1, Z sub 1, T sub 2, so on and so forth. All right, so turning to well-formed formulas. All right, so another way, or a shorthand rather, for well-formed formulas is WFFS. Any sentence, well-formed sentence, is going to be a well-formed formula. So A is a cube is an atomic sentence and it's well-formed formula. But this is not a sentence, since we don't have an individual constant that we're asserting a proposition, or that we're asserting a property of. It won't be an atomic sentence. However, it is a well-formed formula. So as long as we are obeying the very same sort of rules for making a good sentence with individual constants that don't have the operators yet, if we use that very same formula but instead replace them with variables as opposed to an individual constant, then we still have a well-formed formula. When we now have a quantifier that's operating on a well-formed formula, then we have a quantified sentence. All right, so let's talk about the concept of a quantifier binding variables within its scope. So let's start off with the idea of the scope of a quantifier. A scope of a quantifier is going to be determined in a couple of ways. Either it's operating merely on an atomic well-formed formula, in which case the scope ends at that well-formed formula. So this quantifier here is operating on this atomic well-formed formula, and it's succeeding to bind this variable. You might think that in the second case that our quantifier's scope extends all the way out here because we have two variables that are the same, but it's not. Just like in the former case, this quantifier is only succeeding, or the scope of it is only going out this far, and therefore it only succeeds in binding this variable. This variable is not bound. Now, if we had parentheses, one here and one here, then that would tell us that the scope of our quantifier extends till the end of that last parenthesis. So that's how we could get it to extend out there, in which case this single operator would be binding this variable and this variable. Okay. All right, so similarly in this case, because we have the parenthesis here that extends all the way out here, this universal quantifier is binding this x and it's binding this x. So the scope of this quantifier is extending all the way out here, whereas the scope of that existential quantifier is extending out here and it's binding this y. All right, so that reads as for every object x, if x is a cube, then there exists a y such that x is to the left of y. In the next case, our universal quantifier here only extends out to here because we don't have the parentheses that allows it to extend all the way over the well-formed formulas in question. So it succeeds in binding that variable, but it does not succeed in binding this variable. It turns out that the second x there ends up being free or unbound. With this existential quantifier, its scope extends out to here, because the parentheses tells us to extend it all the way out there. It does bind this variable, but since it's a y, it doesn't bind the x. All right, so let's turn to talking about the notion of a bound variable in a little bit more detail. So loosely speaking, a variable is bound if it is associated with a quantifier, otherwise it's free or unbound. So we've got a series of examples here that can help us get an intuitive feel for when a variable is free or when it's unbound. I'm sorry, when it's free or when it's bound. So in this first case, we have no quantifier whatsoever with that well-formed formula x is a cube. So in this case, x is free or unbound. But if we take that very same well-formed formula and then put a quantifier out in front of it, because that well-formed formula is now within the scope of that quantifier, x is bound. Okay, if we have a couple of variables within the scope of a quantifier, as we do in this case, different types of variables, this will be bound. But since we don't have a for all y or a there exists a y, that variable ends up being unbound or free. For that quantifier, that's completely within its scope. And for this quantifier, this is within its scope. So the x associated with the existential quantifier there does bind that variable, and the y of this universal quantifier binds this variable. So x and y are both bound in that case. In this case, the scope, because we don't have the parentheses of this quantifier, only extends out to here. So this x is bound. However, this x, even though it's the same kind of variable, is unbound. We can get them both to be bound, however, with a set of parentheses. Now they're both bound. Alright, so with that under our belt, let's turn to the semantics of our quantifiers, or the meaning of our quantifiers. To put it informally, the truth of a quantified sentence is determined by whether all objects of our domain, when we're talking about universal quantifiers, or whether at least one object of our domain, when we're talking about existential quantifiers, satisfies the well-formed formula that's within the quantifier's scope. Quantifiers or quantifiers, plural. All right, so that means we're going to need to know what this idea of satisfaction or satisfies means. So an object, let's call it A. So an object A satisfies a well-formed formula S of X, whatever that well-formed formula is. Could be X is a cube, could be X is a cube, or Y is a tet, so on and so forth. Okay, so an object A satisfies a well-formed formula S of X, in which X is the only free variable, just in case S of A, so when we substitute A in for X, where A replaces all instance of the free variable X, is true. Otherwise, the well-formed formula is unsatisfied. So satisfaction, if you'll remember, we'll have a domain of objects that we're discussing. We'll have some sentence that's quantified. That's a quantified sentence. So there, that says there exists an X such that X is a cube. We then take, we just give these arbitrary names. They could be A, we could call them N sub 1, N sub 2, N sub 3. Let's say we've got A, B, and C. We then take A and we substitute it in for every instance of X that's within the scope of the quantified sentence in question. and then we check to see whether this is true or not. If it's true, then A satisfies that. In the case of, well, we'll get to the semantics of the existential quantifiers here in a moment. Okay, so in that domain that gets satisfied. But if we had a different domain, in which everything that was in it was a tetrahedron, then there's no object. A does not satisfy this well-formed formula, B does not satisfy it, and C does not satisfy it. Okay. All right, so FOL does not require that the objects in our domain actually have names, so we can just give arbitrary names to objects. N sub 1, N sub 2, N sub 3, you'll see in Tarski's world, is used to do that for unnamed objects. We assume that every domain has at least one object in it, and we assume that every individual constant does in fact pick out an object in the domain. All right, so let's now turn to the semantics specifically for the universal quantifier. All right, so here is the meaning of our universal quantifier. A sentence of the form for all x, s of x is true if and only if every object of the domain in question satisfies the constituent well-formed formula that is s of x. So, if our well-formed formula is x is a cube, and we have the quantified sentence for all x, x is a cube, that's true if and only if every object in the domain is a cube. So if this is all of our objects in the domain that we're talking about, and if go with me on pretending that those are cubes, then because when we substitute each of these names in for the x and see whether they're satisfied, since A will satisfy A is a cube, since B satisfies B is a cube, and C satisfies that A is a cube, then this sentence will be true. But if C is a tetrahedron, then it's not the case that every single one of the objects in the domain satisfies the well-formed formula in question. C does not satisfy it since C is not a cube. So then this sentence would be false. Okay, let's look at another example. For all x, if x is small, then x is a dodecahedron. Pretend that this is a dodecahedron. Okay. And let's suppose that these are all small. So since if we plug in A for these x's, it'll turn out that the consequent is true. I'm sorry, the antecedent is true, but the consequent is false. Meaning we found one counterexample. We found one case in which something is small, but not a dodecahedron. So it'll turn out that this sentence is false in that case. However, let's say those two cubes were large. then when I plug in A, since the antecedent would be false when this is an A and this is an A, and the dodecahedron is also false, it'll turn out that that conditional is true, and therefore A satisfies it. Same thing with B for the same reasons. And C will also satisfy it because C is small. This will turn out to be true. And C is a dodecahedron, so this will turn out to be true as well. So, such a sentence as for all x, if x is small, then x is a dodecahedron is true if and only if for every object in the domain, it is either not small or it is a dodecahedron, at least one of those two. All right, so we can also think about the semantics of the universal quantifier in terms of the Hintica game. So if you commit yourself to for all x s of x, then you're committed to every object in Tarski's world satisfying s of x. If you commit yourself to for all x s of x being false, then you are committed to at least one object not satisfying s of x. There's got to be at least one in the domain that does not satisfy it if you say that it's false. All right, let's turn to taking a look at the semantics of the existential quantifier. All right, so here we have the meaning of the existential quantifier. A sentence of the form there exists in x s of x is true if and only if at least one object of the domain in question satisfies the constituent well-formed formula s of x. So here we have a sentence, there exists in x such that x is a cube. Our well-formed formula corresponding to s of x will be x is a cube. So if we have a domain that we're talking about where we only have tetrahedra, when I plug in A into x is a cube, it's false, so it's not satisfied. When I plug in B, it's not satisfied. When I plug C in, it's not satisfied. And since there's not any one object in the domain that satisfies that well-formed formula, this sentence is false. But in this case, if I have at least one cube, then even though A doesn't satisfy the formula and B doesn't satisfy the formula, C will. And this will then be a true sentence. All right, so now looking at the second example, there exists an x such that x is small and x is a dodecahedron. We have the well-formed formula corresponding to s of x right here. X is small and x is a dodecahedron. So we need to find an object that has the property of being small and being a dodecahedron. So if we look at the domain already set up here, A is neither small nor is it a dodecahedron. B is neither small, well, let me stipulate that these are medium. B is neither small nor a dodecahedron, and C is neither small nor a dodecahedron. So in that domain, it's false. But if at least one of my objects pretend that this is a dodecahedron, even though it's some weird shape. And I'm just going to stipulate that it's small. Now A, being that it's small and that it's a dodecahedron, does satisfy that, and since we have at least one object in the domain satisfying it, instead of being false, this sentence will be true. Alright, so we can think about the semantics of the existential quantifier in terms of the game rules of the Hintica game. So if you commit yourself to there exists an x, s of x, then you're committed to at least one object in Tarski's world that satisfies s of x. But if you commit yourself to there exists an x, s of x being false, then what you've committed yourself to is that there are no objects at all satisfying the well-formed formula s of x, whatever that well-formed formula is. All right, so now that we've talked about the semantics of the universal quantifier and the existential quantifier, let's play around with it in Tarski's world, playing the Hintica game, and see how the Hintica game works with the quantified sentences in Tarski's world. All right, so we've got some sentences here, 4 sentences, and we've got a few worlds as well. So this first world that I have, this first sentence says of it that for all x, x is small. So it has to be the case, since it's the universal quantifier, in order for it to be true, all 3 of these objects need to satisfy this well-formed formula. Turns out this one is small as well as this one. So it should come out to be true, which case it does. But if I say that everything is small in this world, we have one medium object and we have 2 large objects that do not satisfy the well-formed formula. So it should come out to be false, which it is. Now if I say of this world that for all x, if x is large, then x is in the same row as C, you might be tempted into thinking that it's false because there's nothing in this world that is large at all. However, in order to satisfy this conditional, this well-formed formula that's a conditional, either for each of the objects, either it needs to make the antecedent false, or, in the inclusive sense of or, it needs to make the consequent true. Since each of these are small, each of them make the antecedent false, and as a result it satisfies, each of these objects satisfies the well-formed formula, and it's going to turn out to be true. Now you might think that this sentence is false in this world because there are some objects that are not large, namely C and this object, the dodecahedron, as well as this tetrahedron here in the corner. However, because this is small, this object small, and this is medium, they each satisfy this conditional statement, since it makes the antecedent false when we plug them into it. These make the antecedent true. However, we see that both of them are in the same row as C, so the consequent ends up being true. So this statement will end up being true in this world. It says that all large things are in the same row as X. If we look at this world, in the 4th sentence, it says there exists an X such that X is smaller than B. Looking at B, it's medium. Looking at this object, it's small. So this object is smaller than B. And all we need is one object to satisfy this well-formed formula in order for the existential sentence, the existentially quantified sentence, to be true. So this will turn out to be true. This says there exists an X such that X is medium and X is a tetrahedron. So it's saying there exists something that has the property of being medium and the property of being a tetrahedron. B is a tetrahedron and it's medium. So in this world, this sentence will turn out to be true. However, there's no medium tetrahedron in this world. It's false. There's not even a B in this world. So it's going to give us this plus sign because, as we said earlier, FOL is going to make the assumption that when we have an individual constant that it actually picks something out in the world, but it's not doing so in this case. If I make this B, the sentence will turn out to be false. However, if I make this B, then it'll be true because there are objects that are smaller than it. All right, let's go back to this world. Here, if I move one of these blocks up so that it's not in the same row as C, then this block here will make, when we plug it into this well-formed formula, it'll make the antecedent true, but the consequent false. And that's precisely the instance in which a conditional would not be satisfied. Well, the conditional would be false, and since it's false, this well-formed formula is not satisfied by this object. So now, it's not the case that every one of our large objects is in the same row as C, so it'll turn out to be false. And of course, since we have large and medium things in this world, it's not the case that everything is false. Or, I'm sorry, it's not the case that everything is small, so it'll be false. Alright, so let's look at the Hintica game with some of these. Let's say that we commit ourselves to everything being small being true, just to see what happens when it proves this wrong. So notice it's going to tell me that I believe every object satisfies this particular well-formed formula. And it's going to try to find a case that proves me wrong. So it gives an arbitrary name in sub 1 here, so that we can tell what it's talking about. And now it's asking me, do I believe that in sub 1 is small? Let's say I say it's true. I've lost because, of course, in sub 1 it's not small, it's large. Let's say I was to say that it's false. So I believe that some object does not satisfy X is small. And now I have to pick one that doesn't satisfy it. Well, let's pick this dodecahedron. So now it's named it n sub 1 for me. So I believe that's false, that it's small, that n sub 1 is small. Yes, I've won because indeed it is not small. All right, let's play the game with the second sentence. Alright, so let's commit ourselves to this being true, even though it's false in the world at the moment. So I believe that it's true. So I believe that every object satisfies that conditional. So it's going to pick one that does not satisfy it, since it can. Notice that in the same way that it was testing conditionals, it rewrites this into the logically equivalent disjunction. Either the antecedent is false or the consequent is true. Alright, so it picks up n sub 1, so I believe that it's true that either it isn't large or it's in the same row as C. If I say OK, it's going to say, okay, so I must think one of those disjuncts is true. Doesn't matter which one I pick, because I'll turn out to be wrong, and I've lost. Let's try true again. Alright, so I believe that at least one of these formulae is true. Either B isn't large or B is in the same row as C. So I'm going to try, so I'll try to choose a true formula, and I'm going to pick that B is in the same row as C, since B is in fact large. I win. If I was to pick that B isn't large, I'd lose. But it would let me know that I could have one. Alright, there exists an X such that X is smaller than B. Let's say I was to maintain it that is false. Since I think it's false, I don't think that there's any object whatsoever that satisfies it. So then it's going to pick something that does satisfy it, since I'm wrong. And it says, so I think it's false that n sub 1 is smaller than B. Let's continue with that, and it'll let me know that I've lost, because indeed n sub 1 is smaller than B, since n sub 1 is small and B is large. Let's say I maintain that it was true. Alright, so now what I have to do is choose a block that satisfies that well-formed formula, that X is smaller than B. I'm going to choose this dodecahedron. It's going to label it n sub 1, so I believe that n sub 1 is smaller than B. Yes, I do. I win. Alright, I think that probably gives you a good sense about how this game works when it comes to the universal quantifier and the existential quantifier. Alright, that ends this video on the semantics of the quantifiers. I hope it proves useful.